In this section, we're going to talk about three different root finding methods. Those methods are the bisection method, the secant method, and Newton's method. You don't have to write those down now, you will see them as we go. So a root finding method is a way to figure out the zeros of a function. It can also be used to solve equations. You just have to move everything to one side and set it equal to 0. So essentially you're, again, finding a zero of a function. For our first example, let's look at the function x squared minus 7x plus 8. If we graph this function, there are two roots that we can see. It's a parabola, so we know there's either going to be 0, 1, or 2 roots. And these two roots, one of them lies between 1 and 2, and the other one lies between 5 and 6. And if we scroll down, we can see that Wolfram Alpha gives us an exact form for the solutions to this equation. So it gives us 7 halves plus root 17 over 2 and 7 halves minus root 17 over 2. We have something called the quadratic equation that can solve any quadratic, like this particular example. So it's not too difficult. Wolfram Alpha can get an exact form, and you probably wouldn't necessarily need to apply a root finding method in this particular case. However, we also do have some more complicated functions where we don't have a method just readily available to us, like this quadratic formula. So a root finding method is a good way to find an approximation of the actual values of the roots. So in this next example, we're going to consider a quintic polynomial. So that's a degree 5 polynomial, and we're going to look for the root. It just has one in this case. And with quintic polynomials, we don't have something like the quadratic formula where we can just apply it to any quadratic polynomial and get an answer. So Wolfram Alpha actually is going to use some sort of root finding method in order to tell us the answer. So we can see in this graph that the root is somewhere between 2 and 3. Scrolling down, we see an approximation for this solution where x is approximately 2.3 and so on. You will also notice there are 4 complex solutions. I've only thrown them in there because if you do plug something like this into Wolfram Alpha and see complex solutions, I don't want you to be concerned. These are the imaginary solutions. They're not going to show up on our real graph. So we have one root and we see that it's not written in an exact form like it was in the case of the quadratic equation that we showed previously. And we actually find that if we go and click the exact form button on the Wolfram Alpha page, it still doesn't give us an exact form. It just tells us that x is the root of x to the 5th minus 11x squared plus 2x minus 11 near, and then it tells us our approximation. So what this tells us is that Wolfram Alpha doesn't have an exact form and that it is finding this root through some sort of approximation method. These root finding methods, if used correctly and your function's not too wonky or something, they can pretty much approximate any of your roots to as many decimal places as your heart desires, assuming you have, the computation time and the memory and so on. Like if you want to calculate something to 7 trillion decimal places, you may have some limitations because of your computer, but theoretically, given enough computational power, these methods should generally be able to give you an approximation of your root to however many decimal places you would like. Another application of root finding methods is, say we have an equation that we want to solve. So, for example, we want to solve the equation cosine of x equals x to the 8th minus 4. If we graph these, the solutions to this equation is the points of intersection of these graphs, and we can see on this picture that the points of intersection appear to be symmetric, one positive, one negative, and both are 1 point something or negative 1 point something. Now, if we scroll down and look at the exact solutions to this equation, what we see is that we get answers of negative 1.2 and so on, and positive 1.2. But maybe more interesting part is the fact, no, definitely the more interesting part is the fact that x is given as not in terms of the equation that we initially put in, but x is described as the root of some other equation, x to the 8th minus cosine of x minus 4. So Wolfram alpha has taken the question, or the equation that we've given it, and it has changed it into a root finding question in order to figure out the values for x. So essentially what we're doing here is we are finding the root of an equation. Wolfram alpha is taking this equation that we have here, subtracting cosine of x from both sides. Kind of, you can see that it lines up to both sides, maybe. So we're getting 0 equals x to the 8th minus cosine of x minus 4. And then Wolfram alpha is going ahead and using a root finding method on this function right here instead of solving the equation. So these are the basics for what a root finding method is. As I mentioned in the beginning of the video, we will cover 3 root finding methods in detail so that you can use these in order to calculate approximate values for roots. And these 3 methods are going to be first the bisection method, then the secant method, and then Newton's method.